Hi, everybody. Welcome. I'm glad the warm weather has returned. And we are on lecture 7 today. We are going to be moving from elastic deformation to plastic deformation. And we had sort of a theoretical framework in the last lecture on how that happens. And so today we're going to walk through an example problem. This is in the textbook, but this is a very classical problem of a pressure vessel, and we'll talk about first what you may already know, which is at what pressure or what conditions will it yield, and then we'll move past that, and we'll say, okay, well, if we keep pressurizing the thing, under what pressure will it experience a plastic collapse, right? Could we expect a rupture? And so it should be an increased pressure from when it started to yield. And so we'll see exactly how that happens today. I just want to see briefly, show of hands, who has derived these expressions of stress in a pressure vessel in the past. Okay, so like 2/3 maybe? Okay, so give me about 15 minutes and then we'll move beyond the elastic solution. But for those of you who haven't seen this, it's a classic problem. Because there's only one input. It's the pressure inside the vessel. There's a certain geometry to the vessel, and the stresses are very easy to define. So it's a nice classical problem. Also, coincidentally, this problem was on one of my qualifying exams for my PhD. So I have fond memories of this classical problem. All right, so let's draw sort of a cylindrical pressure vessel. Like this. And it's going to have some, let's say, nominal radius, R0. It's going to have a wall thickness that is not very thick, but there's a very thin wall to this pressure vessel. Let me change colors. Go. And so that thickness, starting out, will have a thickness T0. And the pressure vessel will have a length L. And it kind of gives you a hint, L is really not going to change much. Hi.
Actually, I'm just looking for the keys. Is there any keys?
Keys. There were some in the middle of the class? Yeah, go for it. Okay, so what we're going to do is look at an element on the outside of this pressure vessel, or actually through the thickness of the wall. And so let's take an element out of the middle right here. Okay. My 3D drawing is not that great, but you can tell that it's supposed to be sort of a piece of that cylindrical wall. And we're going to define a couple of directions here. So around the circumference of the pressure vessel is going to be our direction number 1, okay? So in 3D space, that's a single axis that goes around the pressure vessel. And we're going to call that direction 1. And correspondingly, that's going to have a stress that goes around. We'll call it sigma 1. Okay, a little bit of a preview there. And then in the longitudinal direction or axial direction along that pressure vessel, that will be, it's perpendicular to the first direction. So we'll call that sigma 2. And then coming directly out radially from the pressure vessel, we'll have a third vector, and we can call that sigma 3. Okay. And so locally we can kind of define x, y, and z, but in this case they do line up with the principal axes, so we're going to call them sigma 1, 2, and 3. So the first question we're asking is, at what pressure, what internal pressure, will this vessel yield? Okay. And we have to assume some things about this pressure vessel, that it is the geometries are perfect. It's constructed in such a way as we don't have any weakness in the welds at the ends. and it's uniform material throughout, homogeneous. And so we have to make those assumptions when we're solving for this. And then, of course, later on, if you have a specific question, you can check some of those assumptions and things. But for now, that's what we have to assume. So now let's define the stress state, or we'll come up with some expressions for sigma 1, sigma 2, sigma 3 in terms of the interior pressure. So the first thing that we'll do is define a hoop stress, and that's going to be sigma 1. All right, so let me write that here. Hoop stress. And goes around the circumference of the pressure vessel. And we're going to get that by doing a sum of forces, right? Simple sum of forces. So let's look at a side view cross section of the pressure vessel. Okay, it's not perfect, but it's okay. It's not bad. Okay. So if we draw sort of a little rainbow outline, that's going to be a cross section if we were to sort of chop this thing in half. And so the hoop stress acts on these locations here, sort of coming out of the bottom of the rainbow. And then what reacts that is the internal pressure P, right? And so that's pressing on all of the interior of that pressure vessel. And we've cut it in half so that we can define the hoop stress, right? If we looked at the full cross section, the full circumference, we don't know what the stresses are around that hoop. So we're going to cut it in half, so we're just looking at the top half. So then if we sum the forces in the one direction, kind of around the hoop, right, that on this schematic that I've drawn, that's kind of a vertical direction, right? And so what we're going to do is sum forces, and each force is going to be stress times an area, stress times an area. Our first stress is sigma 1, right? And that's acting downward at the bottom of the rainbow. And the area over which sigma 1 acts is 2 times the nominal thickness, T naught, times L. Okay? So let's imagine now that this is not, that we've cut it in half and it's a cross section, but it extends all the way along L, right? So it's kind of like you're walking on a covered awning and the awning is a semicircle above you. And so it's the whole thing. And so sigma 1 acts on that little edge downward, and the area of that edge is 2 times the thickness, right? There's 1 on each side, times the entire length, right? So it's just the bottom faces there of that half cylindrical dome. And then counteracting that, and so that's kind of a direction downward, so we could make that, let's make that minus, okay? And then acting upward is going to be the pressure, right? The internal pressure acting upward, so that's P. That has units of pressure. We also need another area to multiply that by. So the area for that is the diameter times the length. So it's basically the projected area of this half cylindrical dome if I'm looking upward. It just looks like a rectangle. And that rectangle is going to have dimensions 2 times R naught times L. All right, so the diameter, or 2R, times L. And so if we do that, we can come up with an expression for what is sigma 1, right? We put, we put the first term on the other side, the L's cancel out, and we end up with, and the 2's cancel out, we end up with the pressure times R naught divided by T naught. Okay. So that's a very helpful expression. R naught given, T naught given, those are geometric. We pump it up to some pressure, the hoop stress has that magnitude. So far, so good. Now let's think about the pressure in the longitudinal direction. So I got to go to another slide here. And so we are going to sum the forces now in the sort of 2 direction, the longitudinal direction. So that'll equal 0. And what we have in the longitudinal direction now is sigma 2 And I'm going to draw my same cross section, but now I'm going to draw the full cross section. And so the sigma 2 acts into the board here, or into the page. And so the area over which it acts, we're going to say that instead of doing like a t outside minus a t inside, it's too many variables, we're going to take a mean radius, Rm, and we'll say that this acts over this cross-hatched area, just this edge of 2 pi Rm, right? So that's the circumference times the thickness. Okay. The radius is much larger than the thickness, so we can make some of these geometric assumptions. So we'll say Rm much greater than T naught. So there would be a smaller order term. We're not going to pay attention to that. So if that's one direction, then what's happening inside the pressure vessel, there's still a P that's pushing outward, right, on both ends. So we have minus, it's just the opposite direction, P. And in this case, it's pushing on the area of an end of the cylinder. So the area of a circle is just pi R naught squared. Okay, so we don't have L in this one, and we'll solve for sigma 2. So that equals pressure times R naught divided by 2 times T naught. Awesome. Very, very easy, just a little ratio. And in fact, we're going to take a note right here that sigma 2 is simply sigma 1 divided by 2. And I forgot to say, we also are going to take that the mean radius is kind of equivalent to that initial radius R naught, because they're both much bigger than T. Okay, so we'll take a note that our longitudinal stress is simply half of our hoop stress. Question?
Was the minus p pi r naught squared term assuming there's a cap on the end? I stopped listening for a second. Oh, doing something. Sorry.
Yeah, so this is it's an enclosed cylindrical tube.
So that's
Yep.
the pressure on the inside face?
Yes.
And it's equating to the pressure in the radius.
Yep.
Cool. Thank you.
All right, other questions right now? Okay. And then there is a radial stress, which I failed to mention, in sigma 3. We go back to my picture here. And sigma 3 doesn't actually have a very strong value at all in this situation. So we're going to say that sigma 3 equals 0. And that this stress is happening in only the sigma 1, sigma 2 direction. So it only happens in the plane of the pressure vessel, and it's not happening through the thickness of the pressure vessel. So now we have 3 values of stress. We have our 3 principal stress values. Okay, so far so good. And so in order to calculate when that would yield, we need to apply some failure theory. The textbook is funny that it applies failure theories before teaching them, but only for this example. And so we're going to give a definition that we will predict, or we will state that yielding will occur when some sort of an effective stress, we'll call it tau naught, and that's actually the octahedral stress, and we'll talk about that shortly, not today. When that gets to be greater than or equal to the critical octahedral stress, tau naught y, for yielding, and that has a specific definition here of 1/3 times the square root of 2 times the yield stress squared. And so this octahedral stress, it's kind of an effective stress. This comes from the von Mises failure criterion, if you remember that from other classes. And so our tau naught, this octahedral stress, has a definition of 1/3 times the sum of squares of the difference of the principal stresses. So I'll write that down. So it's kind of like what we were working with before. So sigma 1 minus sigma 2 squared, and then sum onto that, sigma 2 minus sigma 3. So it's all these combinations. And then sigma 1 minus sigma 3. Actually, I'm going to change the order on this so I just stay with the right conventions, 3 and 1. But we don't have sigma 3, so we will cancel those terms out. So here, cancel that, we'll cancel that. Then we'll move forward with a much simpler expression. And recall that 2 times sigma 2 is equal to sigma 1. All right, so we're also going to plug that in and come up with, so I'll write it out here. So tau naught equals 1/3 times the square root of sigma 1 minus sigma 2, which will be 2 sigma 2 minus sigma 2 squared, right, plus, and then we just have sigma 2 squared plus minus 2 sigma 2 squared. All right, so all I did was substitute in so now we only have sigma 2 in our expression. And we'll continue simplifying, so we get tau naught is equal to 1/3 times, if we have a 2 that's squared, that's 4, plus 2 is 6, so 6 sigma 2 squared. And we can pull out 3's and that kind of thing. We'll do that in a moment. And so what our failure criterion is now is when 1/3 times 6 sigma 2 squared is greater than or equal to 1/3 square root 2 times the yield stress squared. That's just from the top of the slide. That's when yield will occur. Okay, good. But sigma 2, like I don't have that as an input expression. What I have as an input is P and R and T. So we're going to substitute that in for sigma 2 next. And you can see that there's some squares that can come out. All right, so I'm going to rewrite that as 1/3 sigma 2 square root of 6. Let me make sure I get it right. 1/3 the yield stress square root 2. Okay. So we can get sigma 2 greater than or equal to, the 1/3 cancel out, yield stress times 1 divided by square root 3. And then substitute in what we have. Sigma 2 is equal to P R naught over 2 T naught. So P R naught over 2 T naught greater than or equal to yield stress times, or yield stress divided by square root 3. And then finally, we'll solve for the pressure here. So pressure would be greater than or equal to 2 times the initial wall thickness, T naught, divided by square root 3 times the initial radius times whatever the yield stress is. Okay. So we've applied a failure theory. And now we can solve for a pressure based on geometry inputs and the yield point of the material to come up with a pressure. So let's just put some values in to get a feel for that. So let's say that T naught is going to be 1/8 of an inch. All right, so 0.125 inches. So fairly thin. R naught is going to be 8 inches. Nope, I lied, 9 inches. So if the radius is 9 inches, diameter is 18 inches, so it's kind of like this size. And our yield stress will be 89 KSI. So if we plug all that in, we get a pressure that will have to be equal to or surpass about 1,400 PSI. So it's a fairly high pressure. It's not like, you know, ridiculously high, but think about like car tires, compressors you might have worked with, building compressed air, right? This is much higher than most of those. Okay. So this is where most of your solutions will end, right? If you've studied failure criteria in the past, because we have decided it's no longer in the elastic range. It's yielded at the outside somewhere, and that's where we stop. We calculate factor of safety and then move on, okay? But in this class, we're going to move past that and determine our next question, which is where does plastic instability occur? So at what pressure does plastic instability occur? So plastic instability means this thing is going to burst. So elastic yield just means somewhere in the material, it's gone beyond the yield point. And if we keep pressurizing it, something bad's going to happen. Well, this is the something bad. Okay. So at what pressure does plastic instability occur? Okay. So I'll tell you sort of the overall approach, and then we will calculate it. Okay. So for plastic deformation, we derived some expressions, right? And it felt like we were kind of floating in theory land, right? Where we talked about Hooke's law, and then we came up with some pseudo Hooke's law expressions for plastic deformation. And so we are going to make use of that today. And so what we came up with was true plastic strain. And then we called that delta. And we came up with some assumptions, like plastic strain is much greater than elastic strain. Like we don't even care about elastic strain when we have plastic strain. So we said that, and then we also said that there was a directional relationship between the principal true shear strains and the principal shear directions for plastic deformation. And so that was kind of a constraint that helped us come up with some expressions. And so we ended up saying that the true plastic strain is some sort of function of material properties, a strength coefficient and a strain hardening power coefficient N. And then we also had that it is going to be a function of some constants that came about due to those constraints we first applied. So that's alpha and beta, we just calculate those. And then the stresses, right? Principal stresses. And in our case, we don't have just principal stress, we actually have the input pressure and the geometry, so we can relate that easily. We are going to say that the relationships between stresses and pressure still hold. So that would be like our sigma 1 equals whatever P R divided by T, and our sigma 2 is equal to half that. Okay. And then the approach that we're going to take is we are going to say, let's go back to our stress strain diagram. Right, so when we talked about this initially, we had, let me change that to a sigma. We talked about true stress and strain, not the engineering stress and strain, but true stress and strain, which means instantaneous areas, instantaneous lengths. And the true stress and strain curve doesn't arc back over and lower in stress before failure. right? It sort of goes something like this. All right, so this is where we're going to have to make use of kind of something we assume about this in order to solve this. Okay? So we've surpassed the elastic regime, right? And we're assuming that the plastic strains are much higher. So now we're working in this regime, and really we're working in the stable plastic regime. So really the yields, the ultimate stress is going to be somewhere here. All right, ultimate tensile strength is going to be somewhere there. And we're working in this area here, right? The stable plastic regime. But when it hits the ultimate strength, that's when things like, there's necking, and that's when the plastic instability truly occurs. So we're going to say that that point where that ultimate stress is defines where our plastic collapse will be. And at that point, it's kind of an inflection point. I didn't draw it very well here, but there's a concave down, and then there's an inflection point, and then we do a concave up, right? And so at that inflection point, we are going to say that the change in stress with respect to delta, which is our plastic strain, we're going to say that if we take the derivative and set it equal to 0, that will tell us where this inflection point is. Okay, so we're making a lot of assumptions, but this is one way to approach it. Okay. There are many other ways in research, but this is one way that is fairly common to derive these things. And so now we're going to change over our terminology, and instead of sigma, we're going to always use sigma primes, because those are used in the text for plastic stresses, and then we're going to use delta for plastic strain. Okay? So now let's embark on this and solve it according to kind of what we set up last time. So I didn't write out all of the expressions that we had last time for sort of the true plastic strain, but I will write some of them out now. So we had delta 1, delta 2, delta 3, and those were the principal plastic strains. Okay? So for the first one, delta 1, there's an expression that defines that, and so it's in terms of what I said before: stress, material property coefficients, and then alpha and beta. So the first term is sigma 1 prime divided by a strength coefficient k to the power 1 over n. And then we have a bunch of these alphas and betas in here. And this is why we calculate an alpha and beta, so we don't have to deal with these long expressions. But it's like alpha squared plus beta squared plus 1 minus alpha beta minus alpha minus beta. And then we got a bunch of powers like to the 1 minus n over 2n. And then we have one more term at the end here, 1 minus alpha over 2 minus beta over 2. All right, so this is an analytical expression, but it just had a bunch of terms in it, so they decided to collapse it down into these non-dimensional terms, where alpha is sigma 2 prime divided by sigma 1 prime. So it's just a stress ratio. Beta is very similar. We're going to normalize that by sigma 1 prime, but it's now sigma 3 prime divided by sigma 1 prime. So for our pressure vessel now, let's start plugging some stuff in so we can simplify these down. So for our pressure vessel, we had a relationship of before sigma 1 is equal to 2 times sigma 2. We're going to assume that still holds, so we'll put a prime on those. So that gives us our alpha, because it's just a ratio between the two. So alpha equals, 1/2. Okay. And beta is even simpler, because our sigma 3 was equal to 0. So if we assume that holds as well, then beta equals 0. Okay, good. So that knocks out about half those terms. So that's very helpful. so if I substitute in this alpha and beta, then I come up with a much simpler expression. So delta 1 is equal to, first term's the same, sigma 1 prime over k to the 1 over n. Then our second term is just 3/4 because of all those fractions. Exponent is the same, 1 minus n divided by 2n. And then our last term is a constant, also 3/4. Okay, so that's pretty helpful. We're getting there. And now we're going to put this in terms of our pressure vessel. So we're going to substitute in, right, sigma 1 prime was equal to, what was it, P R naught over T naught. I think that was it. Yep, okay. So let's substitute that in. Now we get delta 1 is equal to P R naught over T naught times K to the 1 over N. And then we're going to combine the other 3/4 terms. So 3/4. And instead of 1 minus n over 2n, we'll add another one on that, so it's going to become 1 plus n over 2n. Okay. So now what we've done is substitute in the values for our pressure vessel into sort of the derivation for this true plastic strain delta 1. And now we can call this the true hoop strain, right? So this is in our one direction. So this is going to be our true plastic hoop strain. And so if we go back and think about our intuition, okay, if I'm pumping up a pressure vessel, I would expect that the radius of the pressure vessel would increase as the more I pressurize it, and the hoop strain, right, is going to be positive because I'm putting the hoop, the circumference of the pressure vessel, under a tensile stress, which is going to cause it to elongate. Strain is positive, and that makes sense. So this strain, I don't see any negative terms in here. So that kind of gives us a good intuition. There are similar expressions for delta 2 and delta 3. And I'm not actually going to write all of the expressions down for that. Those are listed in the textbook, and I'm just going to write down what they are here. So delta 2 is going to be equal to 0, and delta 3 is going to equal the opposite of delta 1. So it's minus delta 1. Okay. And if we think about that, our 2 direction was the longitudinal direction. And so in this case, our true plastic strain that seeks to elongate the pressure vessel along its axis is 0. So we're not changing the dimension there. Okay, and that makes some sort of intuitive sense because the dimension around the hoop is probably smaller. And then our delta 3, which is the radial direction coming out of our pressure vessel, is the opposite of delta 1. So you can think about this as the thickness of the pressure vessel, right? So if we have I'll just draw like a little circle here with a cross section. So this is our radial direction, right? Our 3 direction. And so you can think of that as changing the thickness of the pressure vessel. So if we're stretching the hoop and our volume of material is not changing, then we must have the hoop itself getting thinner. We must have delta 3 being negative. And so that is consistent with our assumption that the volume of material doesn't change during plastic strain. Okay? So this means our strains sort of equal out. So we have delta 1 has a positive expression, delta 2 is 0, and delta 3 is the opposite of delta 1. So these are our true plastic strains. Okay, so we're getting there, and we can now start to think about that derivative we were going to take, right? We were going to take a derivative of stress. Well, in this case, we have pressure that derives the stress. So we're going to do we're going to take the derivative of pressure now with respect to these plastic strains and see when that's 0, what is the pressure at that point. We'll solve for that pressure. We can't quite do it just yet because we have, if we look up a material, we can get K and N, but right now all we have is R and R naught and T naught. Those are the initial values. If we truly have plastic strain, those are going to change, right? R naught is going to increase to some final R, and T naught is going to decrease to some final T. So we need some expressions in there for how those will change before we take the derivative, because they change as a function of this plastic strain. Okay, so we just have one more step, then we get to take the derivative. So let's go back to our definition of true strains and apply it to a pressure vessel in like a very fundamental way. So along the hoop, true plastic strain delta 1, right? Our definition for plastic strain was the natural log of some final length over some initial length. Well, our hoop is determined by the circumference. So we are going to have a natural log here of our final circumference, so 2 pi r, divided by the initial circumference, 2 pi r naught. And if we take these two outside expressions, if we want to get rid of the natural log, we can take and put both sides to the exponential e. So we can say that r is equal to, whoops, that should be r, is equal to r naught times e to the delta 1. And that describes how the radius is going to get bigger as a function of the plastic strain in that direction, delta 1. And we'll do the same thing for thickness. We'll say that delta 3 is equal to the natural log of some final thickness divided by the initial thickness. We'll put both sides up to the exponential, and we'll come up with T is equal to T naught e to the delta 3. But we want everything in terms of delta 1 when we take a derivative, because we're taking it, that's the one we're taking. So we will put that as T naught e to the minus delta 1. So if we just look at these expressions, right, for R and for T, we'll see that one has a positive power, right? So it's an increasing exponential. The other one has negative, and so it's a decreasing. And so that goes along with the definitions of those plastic strains. Okay, so now instead of R naught, now in our expression we're going to change that to the R that we derived, and instead of T naught we'll change that to our T. And so we come up with this expression here, delta 1 equal to P times R naught e to the delta 1 divide by 4k T naught e to the minus delta 1 to the 1 over n power times that other constant with a bunch of other n's. So 1 plus n divided by 2n. Okay. All right, so now we can solve for P, and then we can take that derivative and see what our critical pressure is. Okay? So I'm going to take this expression and I'll solve for P on the next slide. I'm just going to write it down. So this is going to be sort of our critical pressure for, what do we call it, plastic instability, you can say something like that, is going to be equal to so we have a term out front, 2k T naught divided by, oops, that should be a 4, divided by R naught, e to the minus 2 delta 1, and then we'll have a second term that's a bunch of deltas and n's and constants. All right, so all I've done is solve for P. And then the instability is reached when the partial pressure with respect to delta 1 goes to 0, right? We've also assumed here that it's going to have that plastic instability in the same direction that it had its first kind of yield event. So we're assuming that happens in the hoop direction. Okay. So there's a long expression for taking the derivative of this with respect to delta 1, because we have it in the exponent on the first term and we have it in the numerator of the second term. And so it's just a long expression, and I'm not going to write it all out. But if we set this derivative equal to 0, and then we solve for what is our, I said we were going to solve for P. We're actually not going to solve for P because P is not in there. We're going to solve for this plastic strain for plastic instability. So what is the plastic strain at this plastic instability? And this is, I have not confirmed all the math that the book has gone through, but it's very funny to me when things knock out like this, where it's just n over 2. So it's just our strength power coefficient divided by 2 is the amount of plastic strain that we need in the hoop direction to cause this plastic instability. Okay, so in order to now calculate what is the pressure, we substitute that in for delta 1. So we substitute in delta 1 is equal to this critical plastic strain, which is n over 2. So that's going to simplify quite a few of our expressions. Then we get rid of anything that we can't look up or don't know initially. All right, so I'm going to, oop, there's my 5-minute warning. We're going to get it. We're very close to the end. So let's substitute that in. So our sort of critical pressure here is going to be 2k T naught divide, oops, I keep writing it too, 4k T naught divide by R naught times e to the minus n, and then a bunch of constants. So n divided by 2 times our 3/4 term, 1 plus n over 2n, and that's all to the n power. We got n's everywhere. So this is an expression that we've derived for this pressure. If we keep pumping up the pressure vessel, it's going to experience a plastic instability and basically burst. Right? So we had before our T naught was equal to 1/8 of an inch. R naught was equal to 9 inches. And now we don't care what the yield stress is because we assume that this has already yielded. We're not using that anymore. What we need now is the strength coefficient, K, and the power coefficient from the strain hardening curves. All right, so let's say that this is an SAE 4130 steel. I'm going to write that here, SAE 4130. All right. SAE stands for Society of Automotive Engineers, and it's one of the key societies in the US that helped establish standards for material properties that are used in automobiles and now outside of automobiles. So there's a table in the textbook which is helpful, but what it comes from is the engineering stress and strain on a log scale. So it's a log that the strain hardening behavior follows, right? So we had, so we'll have some like stress is equal to K times delta to the N power. And if we look up what those values are for SAE 4130 steel, we get a K of 154. I ran out of space here. K PSI, so very high. And N equals 0.156. So we could go back and put those into our expressions and then move them forward. Like, what is T? What is our final T? What is our final R? And what is our delta 1, right? We have all of those expressions. We could find those things. But we derived this expression for pressure because that's what we care about. So if we put these four constants into that expression for pressure, we come out with a plastic collapse pressure of 1,455 psi, whereas our yield point initially was about 1,427 psi. So this is a really helpful guideline, right? Okay, maybe we do get a yield. Well, what if we have an issue and the pressure inside this pressure vessel keeps increasing? Well, if it gets up to about 22, 27 higher, then it's going to have a plastic instability, plastic collapse, the pressure vessel will burst. The book makes a nice argument here if you want to read this end of chapter 5. And they say that if you don't do this plastic instability calculation, and rather you just say, well, I'm just going to put in my ultimate strength instead of yield stress into the yield stress equations. Like, that should get it, right? Well, if you do that, if you take the ultimate strength, put it into the yield criterion, which it's not meant to do, you get something that's really high. You get something that's higher than 1,500 psi. And so you would be overestimating failure, right? And so you might think that this pressure vessel is safe and won't experience plastic collapse, but in fact it would. And so don't make the mistake of putting the ultimate strength into a yield criterion, but rather use the proper plastic deformation equations. So we'll have a chance to practice with this on some other geometries on the problem set, but I think I might have 1 minute for questions. No.
Go back up a bunch of slides. You kind of threw out there the R equals R naught e to the del 1.
Yes.
Where did those two equations come from?
Those two equations came from the definition for true strain, right? So for true strain, the question was, where do these exponential expressions come from? The definition of true strain is a natural log of a ratio. So if you basically solve that and take the natural log away, you take the exponential of both sides, and then you're left with this exponential.
End up with an expression for the actual dimension.
Mm-hmm. Yeah.
Okay.
Yeah. Yes.
You have two expressions for delta 1, this one and the one before that.
I have two expressions for delta 1.
To go to the reverse side.
Yes.
But that doesn't depend on the changing thickness of the radius.
So we've taken these exponentials and plugged them in so that we account for the changing dimensions. I see what the question is though. It's like we have multiple expressions with delta 1. So I guess what we want in the end is a pressure. So let me think about that. I may make a post on the discussion board, like why are we not equating this to one of these other expressions? Yeah, it's a good question. All right, thank you.